All right, thank you. My name is Greg Armstrong. I'm a principal system architect with Renesas Electronics. Renesas probably for the OCP community here is probably not as recognizable. Previously we were Integrated Device Technology, IDT. We are one of the largest timing silicon suppliers for data centers. But we're also very used within telecom. So the whole concept of synchronization is of great interest to me. It's my first time coming to OCP, so I appreciate the invite from the TAP community. But what I was going to talk about today is, which some of the topics have already been touched upon, is I called it Synchronizing the NIC. And the reason I did that is, you know, one of the very first challenges I saw when I came and started looking at data centers, especially I'm trying to understand how to get clocking into and out of is it was not going to be easy. And so when the TAP community came about and gave a forum for people to come and talk and contribute, I found it very informative because you started learning some of the aspects of the architecture that existed and then try to figure out ways to build upon that. And you've already heard some great talks. Julian, I loved his talk because he really talks about looking at a problem and trying to find a solution. What's nice about it is a lot of the stuff he talked about, it's not new. It's new for OCP and new for data centers community, but a lot of the concepts and topics have been addressed for many years through telecom. But the difference is a lot of those things were addressed by companies that tried to solve the problem with their own engineering teams, and they went off and tried to solve it. And then over time, they would look at component businesses to try to buy things and say, can you do this function for us, and try to optimize it and go off that. And then, of course, we would bridge out and try to make it so it was more diversified to go into other markets and other things as that. So what we comes down to is, you know, synchronizing the NIC. You know, a lot of people are talking about timing, precision, accuracies, all this stuff. They talk about 1588. I saw someone say PTP, Precision Time Protocol, is synchronization. I'll rock the boat a bit. It's not, all right? Precision time protocol is a means to precisely distribute time, but it itself is not synchronization. Without some sort of control system, a servo loop, or something that is actually making a measurement to your clock, determining what it is, and then trying to reproduce clocks that are traceable to that, that is synchronization. And that is something that if you want to say, well, how do I go off and develop a servo to be used with 1588, and you go and read the standard, you won't find it. And that's one of the unfortunate limitations of it, and it's much misunderstanding of 1588, is people say, well, what's your performance of 1588? And it's like, you can't say that, it's a protocol. Are you asking like how fast I can send time? What do you want, right? I know what they want, but this is the thing that is part of the education. And so some of this is some of the challenges that are coming into the NIC. People are looking at saying, well, I got it. My 5 timestamps, I got a timestamp, I'm running the protocol, so I'm synchronized, I'm good to go. And I made one little measurement, and I could see I'm about 10 nanoseconds, so I must be fully compliant, I'm good to go. And that's not really true. There's a lot of stuff that we have to look at, right? So one of the first challenges with data center compute is, you know, the clocking traditionally is very contained. It's right in the server, right? You've got your PCI clock. We talked about it, it's usually distributed through buffers, goes off to the different NIC cards, things like that. But they're all effectively running on an independent time, right? It's just an oscillator running typically around 100 ppm, and everything is built off that, right? So fundamentally, compute was just computing, right? It's data compute, server, storage, things like that. But when you start having to look at precision and timing requirements and accuracies, what people are really looking for is saying, well, I want to be able to tell when an event occurred in relationship to another event, and I want to make sure we're kind of on the same page. So it's more really of a relative concept, which is one of the things about, you know, you see all these things about, well, I want to be within 1 microsecond or 1 nanosecond and all this stuff. And you sometimes will hear someone say, oh yeah, but that's to UTC. Is it really important to be UTC? Probably not. The advantage of UTC is it's global. It's a time measurement that everyone can kind of lean towards and measure towards, which really means fundamentally you're just trying to find a means to be able to say, well, if I can tell how traceable I am to that, I can then say how I am relative to somebody else that is also traceable to that. And a lot of that stuff is going to be talked about throughout the sessions, although I guess we're pretty much closing it off now, but hopefully you join some of the other talks. But it's really important to understand is, well, what is synchronization then, right? Which is really the big topic. You know, we had all this discussion on synchronization, but I don't think anyone really said what is synchronization. You saw people talk about phase lock loops. You talk about 1588, talk about all this stuff. But I just wanted to quickly say, well, what is synchronization? Well, what isn't synchronization is when you basically looked at, let's simplify it. You could take a clock, run it into a counter, and then you just basically take a snapshot of those counters at any point of time, and you wanted to say, well, what's the relationship between the two? And if they're just kind of running off oscillators, it's what we call kind of like a free running. They're just running off their natural frequencies. Those frequencies are rarely to the precision of 0.00000, right? So if someone says it's a 25 megahertz clock, well, it usually has some sort of parts per million deviation from an absolute source. And most of those absolute sources are like cesium clocks or some other measurement. And you're trying to say, well, how well am I kind of running, or my pace is relative to someone. So of course, as you can appreciate, just like if you had a race and you had two runners, some runners run faster than others, some run slower than the others, right? But they pretty much are all kind of running at about the same pace most of the time, but there's a lot of variation between them. So what does frequency synchronized means, or syntonized you might hear, and things like that? Well, what that means is what we're trying to do is say, well, what if instead of counting at different rates, what if we could actually count at the same rate, right? So let's run at the same pace. All right, so that's what we call frequency synchronizer. So it's basically we're kind of at the same pace, we're running, we're keeping up with each other, but it doesn't really tell you what the relationship is between the two. They could be running at the same speed, but the other guy could be 5 kilometers ahead of you, right? You still have quite a way to make up, right? So that's where phase or time synchronization comes into. It's a way of saying, well, how can, based on some sort of indicator, can we make a measurement and say, well, how close are we to each other, right? And so the most common one that we heard about talking today is stuff like a 1 PPS or a pulse per second. And if that pulse per second is sent to the two counters at the exact time, they could capture it, and you should be able to run something that could keep them to keep pace. So what does that mean when we're trying to look at it for synchronizing the NIC? Did I jump 2 slides or 1 slide there? Okay, just 1. So the big thing about synchronizing the NIC, so it's very easy, and I say that, I know someone will say, well, it's not easy, but fundamentally, it's not hard to get synchronization into the NIC. But the biggest challenge is how do you get it out of the NIC, right? You know, unless you're doing like directly a boundary clock right in the NIC where you have multi-ports and you're just doing that, okay, that's easy. But what if I need to get it to another card or to the host? Or what if I have a time system, a time card running somewhere else on the server that's sitting there? How do I get that time source onto that? And you heard Julian talking about that, saying, well, I have a very good clock here. How do I share it with the rest of the cards in the system, right? So these are the things that are going to be the challenges that we have to look at. And so I'm not really here to talk about, a product and things like that. There's, of course, the PLLs there. That's our stuff, silicon. But what I'm really focused on is let's solve the problem, right? And that's my kind of call is there's all these work streams that the TAP community has bridged off. One of them is the oscillator work stream, right? So this is one where basically people got together and said, all right, we know there's a lot of history here. There's oscillators out in the industry. There's TCXOs, OCXOs, cesium clocks, rubidium clocks. But what does this all really mean to somebody that maybe has to design a system or a NIC card or a server? What does that mean? And so they went off and tried to come up with a bunch of requirements. They pulled in some applications and said, well, where do these different things fit? And we already saw some references to people talking about, type like holdover, things like that, and certain oscillators can give you certain levels of things. So they tried to capture all this stuff, right? And so this was basically a collaboration of different industry leaders that kind of came from different parts. A lot of them were from telecom, because telecom is doing synchronization for many years. Since the days of the first time they digitized telephones, synchronization has been in telecom, right? So you're talking about 30 to 40 years, all right? So it's a very mature concept, but doesn't mean it's easy to adopt to other industries. So that's what we're hopefully going to try to do with the TAP and things like that. The other one which I want to highlight, and this is the one that I really want to focus on and really want to try to get more people to come to, is we have this work stream called servos. So I already talked about, the biggest downside of 1588 is everyone thinks you have 1588, I have synchronization, and you don't. And there's a lot of examples of where servos have been defined, and industries will put together concepts of like, well, what does it mean to participate in a network that is trying to distribute the clock? There's fundamental characteristics that you have to look at, like, well, what's your free running accuracy if you've never seen an external source, a frequency source or a time source? That's what they call the free run accuracy. And it might be like, 4.6 ppm or 50 ppm or 100 ppm, right? They come up with some number, they say, well, this will be the free running accuracy of the clock if no other time source was connected to it. But then typically, like I said, the whole point of synchronization is you're trying to distribute that time source throughout a network to the end application. And so you want to have the ability to be able to measure that or indicate what is that traceability of that clock as it traverses through that going through. And so typically when you look at that, you have to go and say, well, first I have to understand as each node it's traversing over is going to add some noise, right? So that's what they typically call like a noise generation. It could be, just the nature of, even if it's a perfectly stable, clean source, there's always still something that's going to create some sort of noise generation into that clock source, right? The oscillator is going to have a little bit of noise because of temperature changes, right? And as a temperature control oscillator, there's going to be a little frequency deviation that will go trickle out onto the clock. Well, that's going to go downstream and get amplified and all that stuff. It's going to have an impact to your performance. So they'll try to say, well, we need to cap that, right? And then they'll say, this is how you measure it. This is how long you measured it over, and things like that. And then there's going to be the concept of noise transfer, right? So this is the fundamentals of a phase lock loop. A phase lock loop fundamentally is there to say, look at the input source, have a feedback mechanism coming back, look at them, and look at them in relationship to each other, and try to make it equal to 0. And that's all a phase lock loop is trying to do, but that concept is what gives you the traceability to that clock. But you have to measure saying, well, yes, but if there's a little bit of noise on that clock, how long does it take for the system to react to it and realign to it? And so they developed what the concept is called noise transfer, right? And this would be a characteristic of saying, well, if I pumped in a certain level of amplitude noise of the clock, let's say I moved it 100 nanoseconds peak to peak at a certain frequency, how much of that do I want to allow to pass through? And how much of that do I want to attenuate or filter out so it doesn't pass through? And you had some earlier talks from Keyshawn that talked about standards like the ITU-T. So the ITU-T would take all this stuff and model it and come up with different characteristics. And they would come up and say, well, we want to basically model everything that anything under about 10 hertz of frequency of noise, we're going to call wander, which we'll say is that's just the natural effects of the clock that we want to basically track and be traceable to. But anything higher than about 10 hertz, we're going to call it jitter, which is like a high frequency noise, right? Which for most applications, jitter is actually the one that is most fundamentally devastating for a system, especially if you're talking about high-speed SerDes, like 112 gig and things like that. So that's why you hear talk about phase noises and like femtoseconds or picofemtoseconds in terms of phase noise, because it has a devastation. If that edge is moving too quickly, it starts closing the eye of the SerDes, which means you start losing data. So they come up with all these concepts saying, well, of course, high-frequency noises are very bad to trickle through the system because it's going to have impacts not only to what's delivering the clock, but the data, and it's also going to have an impact to the traceability of that clock going forward. So they'll say, well, let's try to eliminate that, right? So that's one of the fundamental things that a phase lock loop does, is you sometimes may hear them called as a jitter attenuator, which means let's get rid of all the high-frequency error and just clean up the clock, resynthesize clocks using the local clock, the local oscillator, local crystal, and synthesize those back to the application, the SerDes and stuff like that. So that's another thing that you have to have defined as a servo to be able to meet and things like that. And then you also heard concepts of holdover. Well, what is holdover, right? What is holdover? A lot of people hear this term and they're like, well, I don't know what it is. What is it? Well, holdover is kind of like a very specific, it's almost like a sub-function of free run, all right? What it is it means, well, if I had a good traceable source that I've been tracking for a long period of time, and it's like, okay, yeah, a good cesium clock there, it's all been great, it's all been happy, but all of a sudden it gets disconnected, you don't want to just go and say, well, let's just fall back to my fundamental frequency of my oscillator, because it could have been running at 100 ppm. Well, that's not good. All of a sudden you're going to have this quick movement and change of your clock. What holdover is, it's almost like a memory. You know, and so what it does is it basically, as you're looking at that clock long term and you're creating like this long term average of what's the changes that's happening over time in relationship to my local clock, let's remember that. So that if I lose that clock, I can kind of continue from where it left off, and now it's my short term stability of my oscillator is what's going to impact the holdover or the frequency at this point. So a holdover typically is specified more in parts per billion, because it's typically a very slow drift of the clock. And that's what parts per billion really means. It's a drift, right? It's unitless. PPB is unitless. If you want to put a unit on it, typically it's nanoseconds per second. So that's a phase drift per second of the clock. So a 1 ppm clock is moving at about 1 microsecond per second away from where it was a second ago. So that's very devastating if you're trying to maintain 1 microsecond of accuracy. I can't drift faster than that. So that's going to be one important thing that we have to do. So these things have to be built upon to define what is a servo. So it's a little bit more challenging than the oscillator one. The oscillator was kind of more of a very closed system of defining what does the local clock do. When you talk about a servo, you're looking at what the impact is from a system level, from the input coming in and the outputs coming out. And so that's why I think more people need to get involved with this. There's definitely historical places we can go and find some of the initial stepping stones. You heard some of it today from the ITUT. Some people talked about boundary clock, class C, and all this other things. These are all terminologies that tie to ITUT, but it really means nothing for the OCP community. So let's find a way to make it more interesting for the OCP community to understand, well, what does it require for me to do, and where does that servo have to exist in my system at the NIC card? Is it in the host? Is there multiple cascading of servos that are working together to get the fundamental application? I'm not going to talk about the Linux application. You know, that was just kind of an example of me once again proving about Linux, sorry, PTP is not synchronization. There's more to it. But the thing I will highlight is what's changing in what some of the openness of this is, you know, what was predominantly more of a proprietary implementation of silicon for timing, where everything was kind of very closed system. People would just kind of use it and just was a black box, magically worked. Well, one thing that 1588 did is 1588 kind of opened up what we call the phase detector of the clock, right? It's a precision measurement of saying, well, what's your offset to the grandmaster? If you fed that into a loop and actually filtered it over time and converged it, it would actually create as a servo. But there's all these great silicon that's been developed over the 30 years of telecom that has this all integrated as part of the silicon. So your clock generation and filtering is integrated into a single device. And so you can push down the concept of servos right down to the hardware, but then you need an interface. Well, the nice thing about Linux is Linux actually defined that interface 10 years ago. They call it the PTP hardware clock infrastructure. And that's a reason I highlight this is I want to say, well, this is a way where you can start saying, well, how can you take further functions of a PLL and maybe abstract it so that it can be used within the OCP infrastructure. And so some of that was even talked about by Julian's talk, you know, about saying, well, what if we want to do precision frequency monitoring? Well, now you're interfacing some components of hardware doing like detection or phase errors and frequency measurements. Well, how do we make that so it's an open interface to do that? So just a summary, you know, there's many ways we can get synchronization into the NIC. I highlighted some there, feel free to read it. But really, to me, the challenge is how do we get synchronization beyond the NIC? And Julian was a great talk. We have to build off some of the capabilities that are being added, like PTM, but we also have to build upon, like the one thing I will advocate right now, please don't use 1 PPS as a means to distribute a clock. 1 PPS is a means to measure a clock. If you want to measure its traceability, try not to distribute a clock. If you can just imagine how hard it is to take a 1 PPS, and let's say you wanted to generate a clock that is running at 10 gigahertz. How are you going to get exactly 10 billion clock cycles in between each of those 1 PPS edges perfectly? It can be done, we do it, but it's not a good way to distribute a clock because that means every node has to do that complexity of trying to recover the clock. So get involved. All right, the TAP session runs every 2 weeks. Great talks there to learn more about timing and synchronization. But really, it's the working groups. Get involved in the working groups. And there's also industry places you can get involved as well. There's the O-RAN Alliance was highlighted today, and also the ITU-T. Those are other areas that you can get into. And there's also the time synchronization network, TSN, time-sensitive networking. That's another area that you can look at to get involved. Thank you.
Thank you very much, Greg.